that the recorder is on. And we'll take a look at a new homework assignment that has nothing to do with sockets. So I'm pretty sure some of you will feel that that's a relief that we are not dealing with sockets anymore for the time being. So that's the new homework assignment. It's based on threads, and it's the program is very simple. Let me just describe it, and because I can describe it interactively a little bit more effectively. So the main program will spin up two different subthreads. Okay, let's say you are one subthread and you are the other subthread, and one will be designated as the first one to go. So let's say you are the designated thread A, so you get to go first. And the program only has to count to 19 or 20. It stops at 20. It doesn't print 20. It starts with 0. So you would print 0. You increment a counter, and then you have to somehow cooperate with thread B, so that you would stop, and then thread B will print 1, and then increment the counter, so the counter will now be 2, and then you would stop and you coordinate with thread A, so that thread A will go again, print 2, and then increment the counter to 3. So you guys have to go back and forth with synchronization until the counter gets up to 20. When it gets up to 20, and you will be the first one to see the value 20, because you are, when you start, it's an even number. So you'll be the first one to see 20. When you see 20, you say, okay, this is out of the range that I'm supposed to print. So you get to say, okay, I'm returning. I'm done. This thread is done. But before you are completely done, you have to make sure that the other thread also has a chance to detect the end of sequence operation. So then you will have to say, okay, thread B, it's your turn to decide whether it's time for you to quit too, and then you just quit. Just return. There's nothing special you have to do. So when it's your turn, as your last turn, you look at the value. It will still be 20 because the thread A is not going to increment anymore. But you just have to check whether it is at least 20. If it is at least 20, you would also say, okay, I'm done. And you can still say, quote unquote, tell the other thread, even though it's not active anymore, to say, okay, you have one last chance to check whether it is it's your turn to quit or not, and then you just quit. So that's the program. It's just counting from 0 to 19 using two different threads, but have full synchronization between the two threads. Are we? Yep.
What's the problem with him just quitting when he gets to 20? I mean, what is
because thread B is going to wait on something to tell thread B it is your turn. Go ahead and continue your operation. So if thread A doesn't do anything to tell thread B you can go ahead and continue your operation, thread B will just be sitting there waiting for something. So when the main program has to rejoin with those two other threads, the main program will not be joining with thread B because thread B is still waiting. It's still waiting for something. Is that okay? Because the two threads need full synchronization. And in order to do that, one has to be blocked, at certain times, until the other thread tells it, oh, okay, you can go ahead and do your thing now. And by default, when one is active, the other one is waiting. So that means in the very last iteration, thread A can see that the value is 20 already, and it's time for thread A to quit. But thread B is still waiting to get authorized to continue execution.
Okay, so what if we were sharing a heap and he frees it at 20? So he has would I just get a seg fault on my end?
Could you just ask the question again? We are not using the heap, but let's just say that we are.
Yeah, so if it was like dynamically allocated and he freed it, what would happen on my end? Because don't we share the heap?
Yes, you do share the heap. In other words, if one thread is using a pointer pointing to an allocated object that the other thread has deallocated at that point, then you will end up with the same problem as a normal program. Because even in a normal program, you can have portions of the program freeing a pointer, but have somewhere else of the program continuing to use that pointer, and you end up with the same problem. But in this case, we are not doing that. We're just using a single counter, which is probably a global variable or a pointer to a global variable, or a pointer to some variable. So you won't encounter the case of freeing and vowing. Are we doing okay so far in terms of the behavior of the program? It's very simple, right? You have two threads; they have to together count from 0 to 20 and exit normally. But the trick is, how do you get these two threads to synchronize? That's the question. Okay. So what we'll do is we'll quickly go through the description here, because we talked about it already. It's just a reinforcement of what I just talked about. So the program is going to call counter, and the source file is going to be called counter.c. If you want to use a make file, go ahead. But this program is so small that I don't think anyone will need to make use header files and separate files for this particular program. You have to use pthread, which means when you compile the program, you have to use a -pthread to make sure it is linked appropriately with the pthread libraries. The main thread starts two subthreads. Both subthreads should use the same function as the entry point. In other words, you do not have one function for the first thread and a different function for the second thread. Okay? You use the same function for both threads, which means you have to utilize the void pointer. When you pass the void pointer, when you start a thread, you have to make use of that. Name the threads A and B, and you can use a struct to store thread-specific properties and use one of the members as for the name of the thread. So a char pointer to the literal string A and the literal string B would serve just fine. The two threads.
Sorry, members of the struct?
Yes. So you have const char asterisk as one of the members of the struct, and have one to point to double quote A double quote and double quote, and have the other one to point to double quote B and double quote. The two threads will cooperate with each other to accomplish the following, which is just what we said. The only part that I did not say specifically is how do you print out the message. You just have to say thread, X is either A or B, and then you specify the value of the counter. Counter equals V, and V can be 0 to 19. And after you print the value of the counter, then you increase the counter by 1. Make sure that the incrementing is done by the threads interleaving with each other. So A, B, A, B, A, B, instead of 20 A's and B doesn't do anything, or something along that line. Excuse me. Each thread should exit when the counter value reaches 20. So you don't print 20, you print up to 19, because by the time you get to 20, then you decide, okay, it's time for me to quit because the value is already at least 20. The main thread merges with the two subthreads when they are done. Now you have to do it in two different joins, okay? So you have to figure out which one you want to join first. It really does not matter, because both threads should terminate in, but the order they terminate should have no effect on, the merge operations. You may assume the global variable counter starts with 0. You can use a global variable, but it's better off when you have a pointer in your struct pointing to the global variable, so that inside the function, you actually do not use a global variable. And the scenario is basically just playing out, how things should happen. Main creates thread A and thread B. Thread B should block even if it gets control first. Thread A goes first, it prints the counter value, increments, and stop. Thread B gets control, it prints the counter value, increments, and stop to let thread A to do its own thing. Thread A gets control, so it would just be A, B, A, B, A, B. And then at some point, thread A gets control, the counter value reaches the limit, which is 20. Make sure thread B is not unnecessarily blocked at that point, because thread B is going to be blocked at that point. So you have to let thread B know and say, okay, I'm done here, but you should go ahead and do your own thing and probably quit too. So after that, thread A will return or quit. Thread B gets control, the counter value reaches the limit. Make sure thread A is not unnecessarily blocked. Now this part, you have to do it anyway. It doesn't do any harm, even though the thread is already gone. It doesn't do any harm to do this part. Thread B returns, main will merge with both threads, and then main returns. Yep.
You say thread B should block. Well, you talk about blocking a lot, but do you mean simply that it shouldn't that it shouldn't act first? Say thread B should block even if it gets control first, or do you also mean that it should somehow avoid using 100% CPU power?
Both, because each thread, only one thread gets to do the print counter value and increment counter. Only one gets to do it one at a time. But you cannot use one mutex for that purpose, because if you use only one mutex, then you cannot guarantee the interleaving. So you have to use two. One mutex per thread is what you need. Is that no?
Don't understand why, but okay.
Okay. Well, let's think of it this way. I'm going to use two marker pens. Okay. So these are mutexes, mutual exclusion constructs. Okay, and that's going to be the focus of this particular program. It's not just creating the threads, but how do you use mutual exclusion mutexes to guarantee the cooperation of the two threads. Okay. With mutexes, there are two basic operations. You can lock it. You can also unlock it. Okay. If a mutex is locked already, and you try to lock it again, then that particular thread will block. Okay. So in this analogy, I can use, if I put it up like this, it is blocked. If you put it down like this, it is unblocked. Okay, we'll just use that, as the protocol. So the two threads, will basically start up at exactly the same time, literally, almost exactly the same time. So main is responsible to create the two threads using pthread_create. But before you do the creation, you have to create these two mutexes. Okay, one for each thread. So whatever thread you designate as the first one, you want to make sure that it is unlocked to begin with. Okay, and then the other one will start with one that is already locked. So in thread A, which is the same function, they both share the same function. So you have to use the data structure to get to which mutex we are talking about. So in thread A, when you get to a certain point, you will try to lock this, okay? But it is already unlocked. So when you lock it, it's pretty easy. It's not a problem, okay? And then what happens is when you lock it, and then you can proceed after that point, then you can go ahead and print the value of the counter, and then increment the counter. When you're done with that, what you need to do is to put this down, but unblock it. Let's see. No, you want to keep this one up. You want to keep it locked, because you don't want yourself to be able to get back into the loop to do it again, because you're supposed to give thread B a chance to do it too. So what you need to do is to say, oh, here is thread B's locked, and you say, now it's your turn. Okay. At that point, after you unlock thread B's mutex, then you will be going back to the loop at the beginning of the loop, and then you will continue with the loop. But guess what? The first thing before you print the value of the counter is you want to lock the mutex, which you cannot because it's already locked. So you'll be blocked, but you at the same time you can execute. So it's your turn to print the value, increment the counter, and then you have to do exactly the same thing. Because right before you can get into the printing and incrementing the counter, you have to lock that mutex. It is already unlocked by thread A, so when you lock it, you can get past that lock call without any problems. So you do your thing. When you're done, you keep yours locked, because you don't want to get back to the loop and be able to print another value right away. So you want to keep this locked. But before you get back to the beginning of the loop, you have to make sure that the other thread's mutex is unlocked, so that he can continue the process in that particular thread. Is that okay? Does everybody understand the basic idea of this program?
I understand the idea. I don't understand how this is going to happen.
How it is going to happen?
Right, with the locking and the unlocking.
Well, we will talk about the abstract data type of mutex. Remember the discussion of abstract data type? So there are two: initialization, destruction, lock, and unlock. So there are four particular methods that we have to understand in order to make this work. But the basic idea is just alternating the lock versus the unlock state of two mutexes. Yep.
So the mutexes are members of the struct?
Yes, pointers to the mutexes will be, or yeah, you need pointers because he needs, thread B needs access to the mutex of thread A and vice versa too. So one can be an actual structure and the other one has to be a pointer because you need to refer to each other's mutexes.
Are we passing these? Is main going to pass them?
You have to pass them, but you're not passing them as a quote-unquote parameter because you have to construct a struct first to store everything that is specific to each instance of a thread. And then everything you have to access from that particular pointer to a struct. Yep.
So to get this down, you have your, just for looking at one thread, thread A.
Mm-hmm.
Thread A's mutex, how do you say it?
Mutex.
Mutex
Mm-hmm.
starts unlocked, for
Correct.
example. Does it go through and does it update the counter and print out the value before it locks itself? Or is it after it locks?
If we look at the pseudocode, I'm going to put the pseudocode into the homework assignment. Because the pseudocode is a little bit out of the scope of this class, because it's, it really touches, operating system theories in this case, so which is kind of beyond the scope of this class. So if I want to use the pseudocode, okay, so I'm just going to start with pseudocode. This just kind of reminds me of a joke that we were talking about today, because pseudocode is pseudo, S-U-D-O code. And Sean was complaining that he got his file removed by running sudo accidentally. It should have given you a warning in Klingon.
Is that what that was?
Which led to us looking for the Klingon fortune files.
Yeah, where's my pain stake? All right, so the pseudocode is, for each thread, this is what you need to do. So you can basically say while the counter of whatever. Now remember, this is pseudocode, so I'm not really using the actual code that you should be using. So while counter is less than 20, do the following. And what follows, which I would use the actual indentation, because otherwise it won't show up. The first thing you want to do is to lock my mutex. Okay. Because when you attempt to lock your own mutex and it is already locked, then it's going to stop right there. It's going to block at that point. It's going to wait until somebody else is going to unlock it. So that's why one thread has to start with the mutex unlocked and the other one has to start with it locked. Otherwise, they will both be blocked, which is bad because then nobody is going to do anything, or they're both unlocked, which means they will go try to print at the same time, which is also bad. So you lock it first, you print, print the value of the counter, and then you increment the counter, and then you unlock the mutex of the other thread, and that's it. That's pretty much it. With only one exception here, because when you get out of the loop, when counter does get to 20, you would have unlocked the mutex of the other thread. So I think that should work. I think that should work. Because that means the other thread will also get a chance to go through this logic. Are we? Yep. Go ahead.
So this, okay. So the thread that we're executing in right now is, see how?
This is the same template for both threads.
Yeah, yeah. And so, but if you were to lock, because you're lock, when you do lock my mutex, right?
Mm-hmm.
You're locking the thread that's currently executing, aren't you?
But that mutex, okay, one thread A has that mutex unlocked to begin with. So the lock operation is not going to block, and it will just continue to go through. Okay. So look at it this way. Thread A and thread B. the mutex of thread A starts unlocked. The mutex of thread B starts locked. That means, when you start up the two threads, it doesn't even matter which order you start the threads, because because of the mutex, the use of the mutex is going to guarantee the synchronization. So thread A, let's say thread A gets control. Thread A gets to the lock my mutex point. Because it's already unlocked, the lock operation is not going to block. It will just change the state of the lock. So now we have both locks, both mutexes locked, which is fine. Because thread A is already executing. Thread A gets to print the value of the counter, increment the counter. At the end of that operation, then it will get to unlock mutex of the other thread, which means this one gets unlocked. Now thread B has been waiting, because thread B gets to the lock my mutex part already. But it has stopped at that point because the mutex is already locked by that time. So as soon as thread A unlocks the mutex of thread B is going to continue execution. But when you continue execution, the first thing you do is to lock the mutex. So now once again we have both mutexes locked, but you are blocked because you're waiting for the mutex of thread A to be unlocked. So you are blocked. The thread A has blocked. But thread B now has execution because the lock operation did not lock, was unlocked because thread A unlocked the mutex of thread B. So thread B now is in execution, print the value of the counter, increment, and then as the last thing that you do in thread B, you unlock the mutex of thread A. So the thread A, after you have been waiting for the lock to be unlocked, now is the time for you to continue execution. And you start with locking the mutex again, but then you will proceed to do the printing, increment, and then do the other thing, so that now you can go through. So it's really just the locks going like this to control which thread has control. Yeah.
So once you execute lock, it's going to keep on executing until it gets to until it exits its.
Until it gets back to lock my mutex, because at that point the mutex is locked already. So any attempt to relock a locked mutex will block. It's at that point you're waiting for the other thread to unlock your mutex so that you can proceed after that point.
Is it wouldn't after we? Oh, we're in the loop. Okay.
Right, because it's in a loop. So after you get through the unlock the other mutex so that the other thread can go, you go back, you check the counter, and then after you check the counter, it is still less than 20. You will go back and lock yourself, and block in the process. Yep.
So you're sitting on the lock line, the lock my mutex, because you're already locking, you're trying to lock again. You're sitting there, you're threading.
Right.
Thread B comes over and unlocks you, and at that juncture, you're trying to execute the lock. It won't actually just relock there.
It will relock right away, but it will
it'll-
also return.
But that'll be acceptable. That will
Yeah. Yep.
it'll move through. I guess the unlock will allow you to then lock. Is that right?
The unlock.
The unlocking you will allow the lock statement to actually execute, and you'll continue
Correct.
on that from that point locked.
Yes. Now
That
let
was
me.
confusing.
Is it confusing? A little
Just
bit.
to think of you sitting there trying to execute the lock statement, and that somebody else can unlock while you're trying to lock. That's kind of weird.
Okay,
in my mind.
we'll just go ahead and write a simple program to illustrate this point. Okay, what I'll do is I'm going to write a program so that it's the same program that you wrote like really early on. It's the echo program. Okay, I read from standard in and I will try to echo to standard out. Except in this case, I have one thread only responsible for the reading part, and I have another thread that is only responsible for the writing part. Are you guys getting the concept?
Mm-hmm.
So now the reading one is going to read, and then it will try to, it will unblock the other thread to try to write that byte, but it will lock itself up again so that it doesn't read another byte before this byte is written. Okay, so we have a similar interlocking relationship, but they are, each one is, its own subroutine in this case, because the logic clearly is different in this case. Each thread has its own logic. Yep.
I think I figured out a good way to explain it.
Mm-hmm.
It's
Go ahead.
kind of like you start out and you go through a gate,
Mhm.
and then you turn around and you lock the gate, and then you just keep walking on.
Exactly.
And then you get, after you go to the end of the while, you get transported back to the inside the gate.
Right, the other side of the
So then
gate.
you try to come and you can't get out.
Right.
And then somebody else, the other thread comes and unlocks the gate. You go
Exactly.
through, and then you turn around and you lock the gate
Yep.
or something.
That is exactly that's a very, very good analogy. Very good. But in this case, you also have to kind of look at this, and you can see that the two threads, they actually hold the key of the other gate, the gate of the other thread. So, thread A only has the key to unlock the gate of thread B, but not itself, and then vice versa. That's a very good way to look at it. All right, so we'll go ahead and write a program so I can show you, what function calls you need to deal with, and also things to watch out for when you perform those function calls. So I think this part is going to be quite useful for your homework assignment. So 2012-04-18, right after tax day. I turned in my tax return, like e-file, maybe an hour before midnight. So now we can push it even more because you can e-file, so you don't have to get to the post office by a certain time.
You know how they used to have the post offices open? People out there I was listening to the radio and they said that's almost all gone because everybody's electronically filing. But
Yep.
you're not looking for some place to put your paper. You're trying to get your electronics.
And USPS, the post office is probably complaining, how this is affecting its revenue and sure.
It is.
All right, so we'll go ahead and write this program. It's an echoing program, and we'll start with main. In fact, what I'll do is I'm going to start with the two subroutines, the two threads. But remember, in this case, I have one function per thread because the logic of each thread is different. In your program, you have one single function, and you have to start up two different instances of the same thing. But even so, I'm going to use the concept of a struct so that you can see how to use that concept to pass quote-unquote parameters to each particular thread. So I would use a struct echoer and put in attributes inside. I have one single char as my buffer because that has to be shared between the two. So I'm going to use a pointer for that buffer. And then the other constructs that I need here, there's not much else that I need. I do need the mutexes. Okay, so we need to look up the type of the mutex. So what you need to do is demand pthread mutex. I think it's init. I did not install the library or the module for mutex. That's okay. You can look it up on the web. pthread mutex _t. That's the type. There we go. So that's the type for a mutex. So what you need to do is to have that thing inside the structure.
You need to include time.h. You need to include time.h.
That's interesting. But I think we can just go ahead and include pthread.h first and see whether that's sufficient. Yep.
I'm finding something weird on the pthreads man page. It says that I think it's NPTL is the original implementation, but that of pthreads for Linux, but that the more modern one is I think called Linux threads. And yet, are you on Debian? So on Fedora and on Ubuntu, they're both using NPTL, which is not supported under the current glibc. And I think this might be a result of pthread mutex functions. I don't have man pages for. I'm wondering if that's maybe not included in it. So we'll see. But
we'll see. Yep. So we'll have one for the read mutex, And we'll have another one for the write mutex. And before we go any further, we can try to compile this program just to make sure that it works. So gcc-pthread-o echo.c, and it worked. So I think we have the library already installed. The header file is definitely there. It's just that the man pages, was not there.
And he apparently has the man pages.
The man pages is a little bit tricky because there are multiple packages for man pages. So it is possible that I have included the quote-unquote development ones, but not the ones that contain the pthread documentation. All right, so getting back to the program, now that we know this part works, we can now go to the main program here. So we'll have two struct. We can have at least one struct echoer, and then we'll call this in lowercase echoer structure. And then we'll also have the two mutexes. So we have pthread underscore mutex t r mutex and write mutex. All right, which one should I lock first? In other words, if I have one thread responsible for reading and one thread responsible for writing, which one has to wait and which one has to go first? The read one has to go first. Okay, so that means when I initialize, after I initialize, I have to make sure the state of the mutexes are correct. So this is a good time to look up another function call, which is pthread mutex init. We want to do the initialize first, and this works. Okay, let me bump up the font size here. So what we need is this one. It has two parameters. The first parameter is a pointer to the mutex itself, and then the second one is a pointer to the attribute. You can pass null for the attribute, so it uses all the default values, which works in this case. By default, when you create or when you initialize a mutex, its state is unlocked. Okay, so every mutex is a lock that is unlocked to begin with. So if you want it to be locked, you have to make that call to lock it up. So translating this back to the program that I'm writing, then I will have to use pthread mutex init, the address of the write mutex. Oh, the write. Yeah, I have to do it to both anyway. So we'll go ahead and specify null for the second parameter to take all the defaults. Do the same thing to the write mutex. But after we initialize both mutexes, we have to lock up one of them. So pthread mutex lock, and we only want to apply that to the write mutex because that's the only thread that should be blocking initially. Are we doing okay so far with these calls? Initialization, making sure the state are correct to begin with. And then we can initialize our echoer program. And in this case, I can have my buffer as a single character because that's all we're going to do is to echo byte by byte, character by character. So it's time to initialize echoer. So we have echoer dash dot buffer equals to the address of buffer. Technically speaking, it is better to use a p as a prefix to indicate this is a pointer, and this is also a pointer, and that's also a pointer. Okay. Because otherwise, it would imply that these are not pointers; they're actual, characters and mutex objects. Echoer dot p read mutex is the address of our mutex. Echoer.p write mutex is the address of w mutex.
2 lines up, I think you need to fix the echoer.buffer. You changed it to p buffer.
Oh, that's right.
No.
Not there.
No, not there.
The other side.
Oh, the other side. Yes.
That one needs to stay buffer.
Right, so now we have the data structure initialized. And it's time to look up more help. We need to use pthread create. And this one is definitely on the in the virtual machine as well. But it's easy to look up the web, because we already know the names of the calls. So in this case, we need to have a pthread object first. And then for the second parameter, the attribute, we can just use null to take all the default values. This one, we have to supply the name or the address of a function. And then for this part, we have to supply the address of the structure that we are creating. Okay, so we'll go ahead and switch back to our source code. And it's time to create pthread underscore t. And we have two threads here. We have the read thread and then the write thread. So we have read thread and the write thread. Now, when you do this, this is only allocating the storage for the data structure. It is not initializing the data structure. This is not C++. So there's no such thing as a constructor to give you a default, thread structure. This is just allocating the storage. So that means, we have to, make that call to pthread create. And for pthread create, the first parameter is the address of the thread itself. The second parameter is a pointer to the attribute that you want to change, but since we're not going to use any special attributes, we'll just apply a null here. The third one is the entry point of the entire thread. I have not written the subroutine yet, but I can just go ahead and kind of imagine what the subroutine is going to be called. So in this case, this is the read thread func, for the function, the entry point. And then the last parameter is the address of the structure that we are passing. So in this case, it is the address of echoer, like that. So that will create the read thread. And then for the write thread, we'll go ahead and just change a little bit of that. And in this case, we're going to pass the same structure because the structure contains information for both of them. But in your homework assignment, you will not be passing the same data structure because each one needs to know the mutex of the other one. Okay, so there are differences between this program and your program in terms of the structure, but in terms of the calls that you have to go through, the concepts that you have to go through, they are very, very similar. Yep.
When you create a thread, are you always passing a structure to it?
Not always. You don't have to. In other words, the fourth parameter can be null if there's nothing to pass to the entry point of the thread.
So why is that even a parameter? I mean, it's like most of the time when you create a thread, you're going to use a structure with it?
It gives you the flexibility. You can pass any amount of information to the thread that you are starting when you have a pointer to avoid, because I will illustrate how we can do that here. Okay, so we'll go ahead and go back and try to at least write up the skeleton part of the entry point. Okay, the type of a thread has to return a void pointer, and then you also have to make sure that it is also taking a void pointer as a parameter. So we have this as my read thread func, and then the only parameter it has is going to be a pointer to a parameter here. All right, and then we can do the same thing with the write thread. So right away we have a little bit of a problem. If the parameter is passed in as a void pointer, how do we get to the buffer? How do we get to the p-read mutex, p-write mutex, and so on?
We have to cast it what you want.
Yep, we just cast a pointer, which is a dangerous operation because every time you cast a void pointer to something else, you have to make sure that you're casting it correctly, because if you cast it to the wrong thing, to the pointer to the wrong type, no one is going to be able to save you. But that's why we like C.
That's why you do it in a virtual machine.
All right, so that's why we will go in here, and you have several approaches. You can do the pointer cast, every single time you access p-param, or you can have a local variable of the right type, so you don't have to deal with all that casting all the time. It's your choice. I personally like to do it this way. So we have struct echoer and then p echoer, and I just do the cast here. So I say struct echoer pointer and p param. So from now on, I can just use p echoer instead of p param. Is that making any sense so far?
Yes.
It seems to be wasting a local variable, but it does make the code easier to do, at least from my How do I redo? Is it R? No.
Undo. You want undo?
Redo.
Oh, sorry.
It's Control R, Control Shift R.
Control Shift R.
Yeah.
Yay! I seldom have to redo. All right. So now we can get to the meat of the program. In the read func, what are we going to do? We have to keep reading. So the first thing we want to do is we stay in a loop. Okay, so to stay in the loop, I need a local variable int, which is our read result. Do while read result is greater than 0, because that means we actually read something. So inside the loop, the first thing we want to do is to say, can I attempt to read at this point? In other words, the byte in pbuffer, has it been echoed yet? Because if it has not been echoed yet, I should not be reading another byte. Is that making any sense? So the first thing I want to do here is to do a lock, which is a pthread mutex lock. And then you have to pass the address of the mutex that you're trying to block. And in this case, it will be p echoer points to p read mutex. That's already the address of a mutex. I don't have to use the address of operator at this point. So that means, if I have already read another character and it has not been echoed out yet, when I get back to this point, it's going to block because the lock is already locked. And I'm waiting for somebody else to unlock that lock to tell me that, yes, go ahead and read another character because the previous one has been echoed out already. But if I did get past this point, it is safe to do the read operation. So read result gets read from standard in, which is file descriptor 0. And I want to read it to where whatever pbuffer is pointing to. So p echoer points to pbuffer. And I want to read one single byte. When read returns, I have a byte ready to be echoed out. So it's time to unlock the other mutex so that the other thread can continue execution. Is that making any sense so far? So once the read thread func is done, we can do the other one, which is write thread func, which is the entry point of that. Oh, I got it already. I just have to fill in the blank. So the other one, the loop is easy to write. Okay, so for the time being, I'll just turn it into an infinite loop because the content of the loop is pretty easy. I can, for the most part, just copy and paste this portion and change the read to write and the write to read. So we'll go ahead and copy 3 lines and stash it here, and just have to go through each and every single line. So that this one will start with waiting for the write mutex to basically say yes, go ahead and continue operation. And then instead of the read operation, and I'll just be lazy here and not check the result of the write operation. And don't do this, when you're actually writing a commercial program. But since this program's main purpose is to illustrate how to use mutex and threads, I'm just not, going to, put more time into this stuff. And then you also have to change this part here so that it is going to free up the other thread so it can read some more. Okay, but at this point, this is an infinite loop. In other words, after you read the very last character from standard in, the second thread will continue. It will just keep going because it doesn't know when to quit.
But won't it be blocked on mutex lock?
It will be blocked, but it's still active. It's still, there. It's not doing anything because, the lock will stay locked because the other one quit before it frees this one.
Oh, yeah.
Right? So it will still be locked, but the thread is still there, taking up resources. It's not, done yet.
I'm sorry, I must have missed it. You said once read result is 0, then it's just stuck there. Is that what you said?
Say again?
When is it just stuck there forever once read result is 0?
Because what happens is when read returns 0, the read result would get a 0.
Right.
it will free the right mutex one last time, which is probably not a good idea. So I should probably block that one. So I would say if read result is greater than 0, and only in that case I want to unblock the other one, because only in that case I have a character to print, because if this doesn't happen, then the other one doesn't have anything to print. Now, one really quick way to fix this problem so that the other one also knows when to quit is to do this. Make read result a part of the structure. So now they can communicate. So now when you're reading into read result, remember to take out the local variable first, because this way then the compiler will complain if you forget to change one of them. If you keep the local variable, then if you forget to change one of them to the property of the structure, then you'll be referring to the wrong thing. It is still there, but it's not useful anymore. So before you do that, you have to take out the local variable so that the compiler can do the checking for you.
So the way that these are communicating is you just pass the pointer into this variable of the structure.
Yep.
So they're really, when they read and write read result, they're really writing to the same place because they're looking
Correct.
at the address and then.
In this particular program, it works this way because I'm passing the same structure to both threads.
Right, right.
But in your case, each thread gets its own structure, and therefore you have to be more careful because for the most part you only want the attributes of the structure to be pointers so they can point to anything you want instead of actual things.
Right.
And I have to change this one to P echo read result. I think I might have caught them all. If I did not, the compiler would complain. Yep.
You didn't make it a pointer in the struct.
But it doesn't have to be a pointer. Because I am passing the same structure to both threads, so it doesn't have to be a pointer. So now in my other thread, I can say, while P echoer read result is greater than 0, do the following. Well, that means it has to be initialized to that first.
Can you do that before you pass the structure to either of them?
What?
Can you initialize it to something greater than 0 before you pass the structure to either of them?
But that would not make any sense either. What? Okay. It really should be checked after the lock. That's an interesting one because I have to. That means the unblock on the other side has to happen anyway. Yeah, that makes sense. Okay, put a do here, and then we just have to protect this particular operation. And also protect the other operation, because if read result is 0 or less, that means I don't have anything to write, and I don't have to unblock the other guy because the other guy would have exited all by itself anyway.
But you said there's no harm in trying to unlock him even if he's gone?
That is correct. Because all you're doing is you're dealing with a mutex. If a mutex is already unlocked, if you unlock it again, no harm is done.
Okay.
Even if nobody is using that lock, the lock can exist by itself even when the thread that was using it is now gone.
Got it.
There's no. Yeah, go ahead.
We know that read result is going to have a value that we've set before we get that to that spot in the code because it's locked until we set it.
Yep.
Okay.
So in my main program, as soon as I have pthread create, the two pthread create, each one will not only initialize R thread and W thread, it will also start the execution of the threads. So at this point in the main program, it is actually it has nothing to do because everything now is handled by the other two threads. So that means it is time for me to have these two threads to re-merge to the main thread, each one at a time. Okay, I don't really care which one first because they will both terminate at the right time. They will both self-terminate under the right conditions. So I need to look up
the main
P.
program sit there and wait for control to be returned to it from the threads?
Nope, the main program is actually can do whatever it wants to do at this point. Let me go back to the program.
But if you don't do anything, isn't it gonna just it's gonna return?
Well, yeah, if you have a return 0 at the end like this, that means the main program will return. But if the main program returns, that means your entire process is going to be terminated.
Right.
So that means those two other threads, even though they know what to do and they want to do it, the program will just quit.
So
Right.
that's why you
Right.
use join.
That's why you use join, so that you don't terminate the main thread until the subthread says, okay, we are all done.
It blocks until they are done.
Yep.
Okay.
Yeah, pthread create is like dropping off your kids at a football game. So you can drive away after you drop them off and do whatever you want to do.
And join is you're waiting for them, right?
Yep, join means you're going to sit there until the football game is
If you
done.
don't join, then they die out there somewhere.
That's right.
Rugby, your kid.
And you can only join with one, you can only wait on one kid at a time, because when you look at the protocol of pthread join, it can only specify one thread at a time.
Then you better join properly, right? Because you're sitting there waiting for B, and A is gonna come back first.
Well, they both terminate under the right condition. That's guaranteed. In other words, the read thread and the write thread will both terminate on their own correctly. In other words, the football game of both kids will end at the proper time, and both kids know where to wait for you after the game. So how you want to pick up the kids after that is entirely up to you, because you know that they will be waiting at the front entrance after the game is over.
But she's right, you could have a dangerous situation where
You
one-
could, yes. Yeah, if you wait in the wrong order, then let's see. If changing the order of the join, can be a problem, that's not possible, because in this case, both of them, you should be able to interchange the order of the join operation, because neither has anything else to do after the terminating condition. So we should not have a case where the order of the join is important.
At least in this.
In this program, at least, right? Okay, so we have to pass a thread, which is a pthread t, and that means it's not a structure. It's probably just an integer. They're using an integer to identify a thread, but internal to the kernel, the integer gets translated into a structure. It's probably indexed into an array of some kind. Getting back to the program. But we'll go ahead and use the join operation here. So we'll join our thread first, and we are not going to save the value. Okay, so the second parameter, which is the arg, I'm just going to use a null here. And let me make sure that we can use a null for arg.
Isn't that's create, right? For join.
Okay, arg is passed as the sole argument of start
create
routine.
Yeah.
That's the return value. That's the return value of the function.
But you're looking at pthread create here instead of join.
Oh,
There.
okay. So the return value is a pointer to a void, which means you can store the return value of the function if you want to. But I want to make sure that we can actually pass a null to arg, and it doesn't say anything.
Where is
It doesn't say whether arg can be null. Oh, okay, right there. If return value is not null, then it will copy the exit status of the target thread. Okay, what this means is, okay, let me switch back to the program. Okay, look at my program. Look at my subroutines here. Read thread func, really has nothing to return, If you want to make the compiler happy, you can just say return null, because I don't have anything to return. And the same thing for write thread func. You can just use a return here. Now, on the other hand, if the thread has a lot of stuff to tell the main thread when it's done, you can make the return null to return a pointer to a structure of some kind. It doesn't have to be the same structure or the same pointer that was passed to you. In other words, the return value or the pointer to the return value has absolutely nothing to do with the argument itself. What this can return can be a different type. You can have this return a pointer to an integer if it is something that's really simple, or you can have this to return a pointer to a structure that is big and has nothing to do with echoer in this case. So this way, the thread has a way to pass information back to the thread it is joining with to say that, okay, I'm done, but blah, 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 blah. These things happened, when I was executing, and I exited, using this status. These things are done, these things are not done, and so on and so forth. You can pass information from the thread that has ended to the thread that is joining.
That's like if your kids want to tell you what happened at the football game?
Exactly. And each kid can have, a different format, can have different things to tell you, because, that it's just a pointer. But you have to remember to cast that pointer to a pointer of a structure correctly, because that's otherwise it's just a void pointer. But in this case, I don't have anything to return, and as a result, when I join the operation, I can say I don't really care. Don't tell me what they are returning. Yep.
Why is it a pointer to a pointer? The return value?
Because it's basically the way of, it's similar to pass by reference, except in C you do not have pass by reference.
So does that mean in your thread function, do you have to dynamically allocate?
Nope, doesn't have to be dynamic. Does not have to be dynamic. In fact, one thing you can do, okay, for instance, if you want to do it this way, you can have, echoer, the structure of echoer itself to contain, a struct for the return value. So if you want this to be done like this, okay, and we'll just put something here, okay, we can say turn, okay, let's say error code of some kind, okay, I don't really care what it is. Then in that case, what you can do is to say, instead of return null, you can have it to return p echoer, what did I use? Return value. But you have to use the address of that. You can do it this way. So where it comes from is not important. You can use dynamic allocation, you can use static allocation, you can make it a part of the argument itself. It doesn't really matter. As long as this still exists by the time you get back to the thread that you're joining with, hey, you can use anything you want. Globals, static local variables, non-static local variables, it doesn't matter, as long as it continues to exist at that point. Are we doing okay so far with this? So even though I'm returning something here, I can choose to ignore it. Now, if I do not want to ignore it, then I need a void a pointer to a void here, so that I can dereference it once to get back to the pointer that was actually returned by the thread itself. That's why you need a double asterisk instead of a single one. It's basically how we do pass by reference in C, the clumsy way. All right, so at this point, I think this program should work, assuming I don't make any really dumb mistakes, which I usually do. Okay, and it's line 39. I forgot to put a semicolon, and typical. All right, so we are running echo. It is echoing. The question is, if I do Control D, does it terminate correctly? And the answer is, it did. So is that helpful? I mean, let me go back to the program so that you guys can tell me whether it illustrates the use of mutex and also threads effectively. Your program.
That was really helpful.
Yeah, and also the process of explaining how the program was designed, and I'm hoping the whole process is helpful. and no one's going to complain and say, Tech didn't prep his class, because he didn't pre-write the code and just slap the code on the screen and say, okay, just copy that. I like the interaction of actually writing code, during the class. Sometimes it doesn't work. Are there any questions though? I mean, let me go back to all the key concepts here.
So in our lab, in our program, we'll be passing both of the mutexes to the single routine.
In your program, it will be similar in a way because you will have 2 threads for sure. Okay, so you will have 2 threads. You probably don't want to name them as read and write threads. I mean, you probably want to name them as thread A, thread B, whatever you want to do it. You also have 2 mutexes. You want to name the mutexes accordingly. And you don't want these mutexes to be in the structure itself. I think it is okay because I think pthread mutex t is actually just an integer, which means it doesn't have to be the address of, but it's safer to use the address of and use a pointer similar to what I have here inside the structure. So inside the structure, you will have 2 pointers to mutexes, one for yourself and one for the other thread, so that you can use the same mechanism that I use here, lock yourself, lock your own mutex so that you don't get into that section of code unless you are ready to. And then at the end of your own code, you have to unlock the mutex of the other one so that the other one can continue execution. Yep.
So would that be part of what we're passing to the thread when we create it? Is your thread is, if you are A, then your mutex is mutex A.
Correct.
So then it knows to unlock the other guy.
Right. You have to initialize these things a little bit differently. Because you have 2 structures to initialize, and then you have to make sure that when you initialize those 2 structures, that you initialize the structures correctly. You don't have buffer for sure, but you have a pointer. And you have a counter.
Okay, so you create the structures, and then when you fire up the thread, then you pass the structure that you want.
You pass
that
the
thread to
address
use.
of the structure.
Got
Right.
it.
But you have 2 structures. Remember, I only have one.
Right.
Because I can use one single structure to share the same structure between the 2 threads. But in your case, you have 2 structures because the what is my mutex versus what is the other thread's mutex. That's the part that cannot be the same, and therefore you have to use 2 structures instead of one.
Okay.
You also only have one single entry point. In other words, you only have one single function as an entry point, but you pass a different structure to it in the 2 different creates, so that each one knows which one it is and what to do, how to do things correctly. But other than that, the structure of this program, for the most part, you can basically just reuse. The difference is, you still have 2 creates, but you will pass different pointers to, the address of different structures. And at the end, you still have 2 joins, and the order of the joins should not really matter anyway, because each one should get out, at the right time on its own, not depending on, is the other one done? They're not waiting on each other, because you're dropping off 2 kids in 2 different soccer games, and when each soccer game ends has nothing to do with when the other one ends. And the kids already know that they have to go to the front entrance after the game ends. So, how you want to pick them up, doesn't matter. Is that okay with this program? I think I just wrote maybe 95% of your code. You can go through a global search and replace. Just change the variable names to the appropriate ones. Change the buffer to counter. Do the increment instead of the read and the write.
Get rid of one of the functions.
Get rid of your program will be shorter. You also need to pound include standard I/O so you can use printf.
Can you do that here to make it easier?
Just put it in comments, right? In your program. In fact, I can probably use a conditional compilation, so you can supply a different conditional, macro. You can turn it from the echoer, into your program and back and forth.
That's awesome.
But is it okay? Do you guys understand the concept of mutex? It's a very, very important concept, for thread synchronization. So I'm going to go back to my homework assignment a little bit here. And we have just enough time to talk about what is a semaphore, which is related to a mutex, but it's not exactly the same thing. So if I go back to my own real-time kernel, it doesn't have a concept of a mutex, but it has a different concept for synchronization. And that synchronization concept is called a semaphore. So I'm just going to look for that, semaphore. So I use the concept of a semaphore instead of the concept of mutex for about the same thing. There's only one difference between the two. A semaphore is almost like a counter by itself. So a semaphore starts with a quote-unquote particular value. You can initialize when you create a semaphore. You can start with 3, 2, 1, 0, whatever. Okay, except for negative values. You cannot start with a negative value. Now the semaphore has two operations, kind of like mutexes have lock and unlock. But the two operations that a semaphore has, one is called a P operation, and the other one is called a V operation. I believe these are the first letter of decrement and increment respectively in Dutch. I think the guy who invented this may be Dijkstra, who's a Dutch. So, and just being curious, we'll go ahead and look up that. Semaphore PV operation. Semaphores. Semantics. See, V is increment and P is basically decrement.
What is it? It says C
Explain.
below. It's, well, I don't know if it's used, but it says C below, and P or weight C below. I guess that's not going to tell you.
Why it's P and V. I think it has the function name. There we go. Initial of the Dutch word. V stands for increase in Dutch, and P stands for to test or to try in Dutch. Okay.
How obscure, huh?
It is kind of obscure, yes. Well, it's an international community, so we cannot always say use the English word for that. So anyway, in this case, we have the P operation, which is almost the same as a decrement or lock, and V is increment, which is almost the same as unlock, except it is more general in this case. What happens with a semaphore is it is quote-unquote a counter. So let's see whether I can have a little analogy of a counter here. I have a little slip of paper, which I would use as a counter. Let's see, that may not work too well. Okay, I'll just use it as a counter. So let's say that the counter starts with a value of 3, okay? Okay, so this is how the counter is initialized. It has a value of 3. When you perform a P operation, which I would call as a decrement operation, if the number on a semaphore is at least 1, then you can go ahead and decrement it, and you are not blocked. So let's say you are a thread attempting to do a P operation on this semaphore, then you can go ahead and change this 3 to a 2, and then you can continue with whatever you want to do because the P operation is not going to block. So from that perspective, it's not kind of like a mutex, because a mutex means if you lock it, then it's done. Okay. Then you can go ahead as a second thread. You can come in, or you can go back and do the same thing. It's 2, and you want to perform a P operation. No problem. We'll change the 2 to a 1. Okay. And then let's say you come back and you want to decrement this one more time, another P operation. It is 1, which is not 0, so you can do it one last time. So now you will go ahead and change this to a 0 without blocking. Okay, but the semaphore now has a value of 0, okay, which is actually quote unquote locked. Okay. Now let's say we have 4 more threads coming in attempting to do a P operation on this semaphore. Okay, so that would be 1, 2, 3, 4. 4 threads try to come in and do a P operation on this semaphore. So when you come in as a thread to try to do a P operation, you cannot do it because the semaphore has a value of 0 already. So what's going to happen is you're going to block. And you come in next, let's say I want to do a P operation on this semaphore. It's already 0. Sorry, you are going to be blocked, and you're going to be blocked, and you're going to be blocked. So now we have 4 processes attempting to do a P operation on this semaphore when it had a value of 0. Okay? Let's say the two of you, now you want to do a V operation. When you perform a V operation, the semaphore value is now 0. So when you do a V operation, it is actually -4 at this point because we have 4 processes or 4 threads waiting on it. So technically speaking, it has a value of -4. However, what happens is when you come in and say, I'm going to do a V operation, the semaphore value of 0 actually doesn't change. But what does happen is I will go to the 4 threads that were waiting on this semaphore, and I will use a queue, first in, first out, to maintain the 4 threads that are waiting on it. So because you are the first one who performed the P operation and was blocked, so you will be the first one that can get past your P operation. And so now you are unlocked and you can do whatever you want to do. When someone else, let's say me, perform another V operation, then the next person who's waiting is going to be, or the next thread who was waiting can now proceed and continue with whatever that thread needs to do. So the concept of a semaphore is almost the same as a mutex, except you don't have just lock versus unlock. It is actually a counter. Okay. Now the 2 concepts are considered equivalent. What that means is you can have a system that only gives you mutexes, and you can have a system that only gives you semaphores. They can implement each other. You can implement semaphores from mutexes, and you can implement mutexes from semaphores. That one is actually pretty easy because a mutex is a semaphore that can only have a value of 0 or 1, locked versus unlocked. But the other one is actually easy to implement as well. You just have to use a few semaphores and a counter to wrap around. So you can implement a semaphore by using mutexes and a counter in a data structure, and it can do exactly the same thing. So are we doing okay so far with these concepts? I think that's as far as I can present it in this class in terms of thread synchronization. I'm not going to get into the. There are interesting problems. I think one is called the dining philosopher problem, where you have philosophers sitting in a round table. And I think in this case, you can either use the Chinese chopstick analogy or the Western fork and knife analogy. But basically, what happens is you only have chopstick works better in this case. So you have 5 people sitting in a round table, and you have exactly 5 individual chopsticks, not 5 pairs of chopsticks, but 5 exact chopsticks. In order for one thread to continue operation, it needs to acquire both chopsticks. Okay? So now you can have a deadlock situation. What if all 5 threads each decide to grab the chopstick on its right? Then you have 5 threads, each one holding onto one single chopstick, waiting for the other chopstick to be available and be able to do nothing. So how do you prevent this quote-unquote deadlock situation from happening? How do you make sure that if a thread cannot get both chopsticks, it will just not do anything? It's like, okay, I see one chopstick on my right-hand side, but not the other one. I'm not going to do anything. I'm going to wait until the other chopstick is also available, because otherwise you can end up with a deadlock situation where one process or each thread has only one chopstick and cannot proceed to do whatever it wants to do with the chopstick and then free up the chopsticks. So I'm not going to talk about that in this class. That's a class that you have to take as an upper division class at a university. It's called The name of that class is going to be very simple. It's usually called the Principles of Operating Systems, or even worse, Introduction to Operating Systems, which has nothing to do with our operating system classes here, where you learn how to use Windows. All right, we're running out of time. I'll see you guys on Monday. And the homework assignment has 1 week. You have 1 week to work on it. I think most of you will be done in 5 minutes. So. Yep.
Sorry for missing the class, and I tried to.
No, because